Yo everyone, this is page 341. No, I did not rhyme one with one. It's Isosceles triangle base angles theorem. Converse. Have your note card ready to go. I caught it, but I wrinkled it. Darn it. Okay, that's okay. It means that I've been using the note card and I can see that it is valuable for information. Today's word for the day is transversal and also that one, supplementary angles. Thank you for checking in. Oh, perpendicular. We should also acknowledge that we're talking about perpendicular bisectors and base angles of isosceles triangles. So let's take a look at page 341. Have a piece of tracing paper. Have your pencil, your highlighter, your other note cards. In fact, specifically for this video, I'm going to be using perpendicular bisector theorem, maybe CPCTC, maybe reflexive property, maybe given, and definitely the isosceles triangle base angle theorem. Today in this video we're talking about the converse. Let's take a look at that one though, right? So I wrote down this statement from page 340 about the direct way that the isosceles triangle base angles theorem is stated. And then I highlighted the if in yellow and the pink is highlighting the then section of the statement. When we want to write the converse, all you have to do with a little wordplay magic is switch the if then. So I'm going to write it pretty much as is. If two angles opposite the sides of a triangle are congruent, right? So if two angles on a triangle are congruent, right? That's pretty much the pink statement. Maybe a little bit like the opposite. I'll probably save that for the next part here. But I got to say, if two angles of a triangle are congruent, then the sides opposite those angles are congruent. Right? This was the yellow statement of the original, and then this up here is the pink statement. It's like you switched, no, it's not like, it is. You switched the yellow and pink highlighted statements. Converse. Well, let's talk about how we can prove that that's actually true, right? Like right now it's just a conjecture. And a conjecture is a fancy word of saying like, I have an idea. But we need a proof of it to turn it into a theorem. Consider the diagram and write a paragraph proof of the conjecture. So let's consider the diagram by zooming in a little bit and moving it around. Oh, also, we're going to do a Mad Lib for a paragraph proof. So pause the video here for, like I'm going to pause myself for 3 seconds, but you need to pause the video and write all that down and then resume the video when you're ready. Write this down in your book. Okay, assuming you paused right there. Hi, welcome back. I'm going to go ahead and actually talk about what this diagram needs to know. So we need to put a piece of tracing paper, and I've kind of gone ahead, like the cooking shows do, right? And I've pre-traced this angle. So I want to make sure you can see that, right? I've pre-traced angle G, and I'm going to create an angle bisector. So the way you create an angle bisector is you trace this line, this is your angle, and you carefully fold the tracing paper so that wherever this point is on one paper perfectly lines up on top of the other points. This line and this line segment will totally perfectly line up. If you're off by a little bit, see, this is not lined up. If you're off by a little bit, if the angle is all messed up, you will not have a perpendicular bisector. You got to make sure that your fold, when you end up folding, this goes right through G, and everything's lined up, and then you get a nice sharp crease on the paper. Open it back up, and on the crease, you have an angle bisector. Let's see here. I gotta make sure it's lined up. On the crease, we have an angle bisector. So I'm going to create this angle bisector on the graph. Flip the paper over, trace over it a little bit. Definitely label right here. We're going to label this C. Okay. And this line, maybe I'm going to bring in my ruler so I can actually kind of like trace it like accurately. Here we go. Precision is one of those skills in mathematics, all right? There it is. We've had it. We have our line that goes from G through C, and we're meant to show that this angle and this angle are the same because it's an angle bisector. Angle G is being cut into two pieces, and those pieces are the same. All right, let's talk about then what the proof is, right? So here's the proof, Mad Lib time, and we're going to also be adding highlighter and markings to the diagram along the way. So have those resources ready to go. Okay, once again, if you haven't paused and written down the Mad Lib, do it now. Okay, highlighter, marking time, let's go. It says that angle B and angle D are congruent, and that's the given. So since it's the given, we need to also acknowledge that phrase. We got to make sure that we are being aware of the given statement, and then you need to go to the diagram and actually put markings on those angles. If you are not processing the diagram, you are not going to be able to understand this. Challenge accepted? No, it's a fact. I've seen it for so many years of teaching geometry courses. Angle B and angle D are the same. Make them look like they have the same color. Because of the angle bisector, I'm going to write that right here, given. Angle B and angle D are congruent. It's the given. Now we're going to construct, and we did, so that's a little bit, after the fact and returning to it. We're going to construct point C on D so that this line segment right here, GC, technically it's a ray, it'll bisect angle G. Always the middle letter. Okay? And it did right there. We have a perpendicular bisector, so this angle, I can't use pink yet. Pink is saved for the prove. Okay? We have, though, that this angle and this angle, those two sides are equal, or they're congruent. So I'm going to list them. Angle DGC. So that's from D to G to C. This angle of this triangle is going to be congruent to this angle, BGC, of this bottom triangle, angle BGC. We've got two angles that are congruent. If we could just get a third statement about a side that was congruent, we would be ready to go. I wonder how it might be proven true that there is a side that is the same on reflexive property is the key word. Oh my gosh, it was there the whole time. Okay, reflexive property means that if there's a side that's shared in common by both triangles, we get to say reflexive property means it's equal to itself. So GC is in the top triangle and GC is in the bottom triangle. GC is congruent to GC, but it's being used in two different places. That's why we need this. In fact, I need to say that we use this when a side or angle is being used in two different shapes. That's also a look for with the reflexive property. We're using the same line, but it's being used in two different shapes. Okay, so that means that we have an angle pair, and we have a side pair, and we have an angle pair. When you can identify three statements, three geometry triangle congruent statements, then our triangles GDC and the other one GBC are congruent by A, S, A. A. Oh, the side is not between the two angles, so it's AAS. Might be a little bit weird to think about right there, but that's what it is. It angle, side, because the side is not between the two angles, so don't put the letter S between the two angles, the two letter A's. Finally, by the vocabulary anagram, what's the word for that? By this, right, we have the pieces are the same, and that which was meant to be proved congruent is GB is congruent to GD. Box. Proof. Add some highlighter to your note card on the isosceles triangle base angles converse, and then acknowledge that the converse is what you get when you switch the if-then statements from the original theorem. Like, comment, and subscribe.